maths educational video. Let's look at two examples on line integrals. One for two-dimensional curves and one for the 3D case. Before that, let's talk about the concept of orientation of curve. Suppose we are given a curve C with the following parametric equations for t lying between two numbers a and b. T equals to a will correspond to the initial point, t equals to b will correspond to the terminal point. The movement from the point A to the point B is what is known as positive orientation of the curve. So when it comes to a space curve, especially in the context of integration, the direction of movement is important. So here's a quick example. C is the line joining these 2 points. But we are specifically talking about 0, 0 to 1, 1. So the direction is as shown in the diagram. So we need a representation that can do that. So in this particular case, Ti plus Tj for t lying between 0 and 1 will give us exactly this direction. So if you need to have a representation for 1, 1 to 0, 0 with the arrow reversed, this particular representation will not work. So you have to try another one. So essentially we want a representation that gives us the direction from the intended initial point to the intended terminal point. Let's look at example 1. This is a 2D case. We have to find this line integral. Integrand is yx plus 1 over the curve, which is, according to the description, upper half of a unit circle. Unit circle means the radius is 1, joining 1, 0 to minus 1, 0. I'll show the diagram later. This is an anti-clockwise movement. But first, let's talk about something more general. Given a circle centered at AB and having a radius of r, this pair of parametric equations will work. The range of t will depend on the initial and terminal points, and also on whether we are talking about a full circle or just a sector of the circle. For example, if you are talking about a complete circle from 1, 0 to minus 1, 0, from 1, 0 to 1, 0, the same initial and terminal point, then this representation will give us an anti-clockwise movement, as shown on the diagram indicated with the red arrows. Now back to this example. The center of the circle is 0, 0. So using the formula you have just seen, with radius equals to 1, we have this pair of parametric equations, cosine t, sine t for x, y respectively. Be careful about the range of values of t. Here we are talking about going from 1, 0 to minus 1, 0. And it's a semicircle. So t will go from 0 to pi. You can always verify when t equals to 0, x equals to 1, y equals to 0. So you do get the intended initial point. When t equals to pi, cosine pi is minus 1, sine pi is 0. So that is the intended terminal point. With the parametric equations at our disposal, we can now apply the formula in the box. Let's simplify the integrand. Within the square root, we have something familiar. Sine squared plus cos squared equals to 1. That reduces the integrand to sine t cos t plus 1. But sine t cosine t can be reduced to half sine 2t by virtue of this famous double angle formula. So in the end, we have half sine 2t plus 1. And this can be integrated easily, giving us the final outcome of pi. Let's look at a three-dimensional example. This time the curve C is actually a straight line joining 0, 0, 0 to 1, 1, 1. So now we talk about general representation. For a line segment joining a point A to a point B, given in the box, we can quickly verify that t equals 0 will give us the point A, while t equals to 1 will give us the point B. Using the formula we just seen, with the coordinates of the 2 points substituted, we end up with this representation, ti plus tj plus tk. So we are now ready to apply the line integral formula. Replacing x, y, and z with the corresponding parametric equations, and simplifying the term within the square root, we can get a final answer of 2 square root of 3 after integrating this polynomial.